Good afternoon and welcome to the digital closing event of both the Profit and the Matter project. My name is Ragaert and I will be your host for this afternoon. Both Profit and Matter have been Catalisti-ICON projects, which are projects in which academia and industry work very closely together to advance the state of the industry. Profit has handled the recovery of plastics from commingled municipal waste and has focused on issues such as odour, separation and contamination. Matter has had a gander at the new P+MD bag, which is being run here in Belgium for new curbside collection of post-consumer packaging waste. We have had a look at what are the qualities of the streams that would be coming from that, and also a lot of attention has been given to the balance between mechanical and chemical recycling. We have quite an interesting program for you this afternoon and also quite a big audience. We have over 150 participants coming from 16 countries. In a few moments, we will start with the presentations of the results, first of the Profit project and then Matter. Don't worry, this is not going to be 2 hours of academics lecturing at you with PowerPoint slides, not at all. We have made quite a good mix between presenters from industry and university, and we have also quite a few nice videos for you. Towards the end of the event, there will be a panel discussion, and we have a diverse panel of experts, all of them with quite a lot of experience in plastics and waste management. Also, you will be able to ask them your questions. Stay tuned for more information on that. And then now, without much further ado, I would like to pass the word to Mr. Nico Kimpe from Vanheede Environment Group. Vanheede has been the industrial project lead on Profit, and he will take us by the hand and lead us into the Profit project results. Nico, please.
Thank you, Kim. Hello, everyone. Welcome here on the presentation. I would like to introduce you to the Profit project. Profit is a project that handles about a focus on recycling plastics and heavy contaminated plastics from installations, from digestion installations. And these plastics are very difficult to recycle, and that's what it handles about. This is the project, Profit here, and we were working there with the ICON Catalisti project. ICON because we have a close cooperation with the industrial partners together with the university partners from the Ghent. And other partners in this project were Organic Waste Systems from Ghent, Govaerts, who is taking the material and using it as a secondary material. The other partner is OVAM, the Flanders government environmental agency, and also Ghent. And I would like to give the word now to Ruben de Metz. Thank you.
Thank you, Nico. I will go further with the technical side of the project. The aim of the project was to develop new value chains for plastics coming from complex waste streams. And a key term here is reverse engineering, in which we focus on the physical properties of the end product. In this way, we will try to recycle and to purify these streams up to a level compared to the properties of these end products. And therefore, we will implement a fit-for-use separation. 2 case study streams were tackled within the project. One coming from separated food waste. The food is in that way separated from the plastics. The organic fraction is sent to anaerobic digestion, and the packaging waste is our first case study. Then a second stream is coming from the municipal solid waste fraction, in which it is derived after going through a Sordicep digestion installation. The waste streams are characterized by a complex composition, and not only a variety of plastics are in there, but also non-polymer contaminants like wood, organics, textiles, stones, and metals. A first research area within this project was the separation technologies. It's important to focus this research on new and innovative ways to separate different plastics. And one such a technique is selective flotation. In this project, we focused on the zinc fraction, polymers, PET, PVC, and PS. The principle of selective flotation, you can see this principle of flotation in the bottom figure. Here, it will be the intention to make one polymer more hydrophilic than the other polymers in the mixture. And it has to be said that in general, polymers are hydrophobic by nature and will therefore adhere air bubbles. Different methods are possible to make one polymer more hydrophilic than the other polymers in the mixture. And this we tackled in the PROFIT project. The first series of experiments were focused on the treatment and adsorption of surfactants, followed by a flotation in water. In the figure on the left, you see the recovery rates of the different polymers studied. And from these graphs, it's clear that separation is possible. And the larger the difference between the different graphs, the easier and the less recirculation of the zinc fraction is needed. A second series of experiments were focused on the flotation medium itself, because this also has an influence on the suppression of plastics. And here we did the flotation in adsorption solutions, in surfactant solutions, sorry. And in this way, we were able to suppress more plastics by this technique. And the third series of experiments were focused on gamma flotation. And this is a phenomenon in which only the flotation liquid is important in the flotation, in the selective flotation separation. From these measurements, it was clear that we could receive a good separation between the different polymers. In this project, it might even be possible to cause a separation between polyethylene and polypropylene. And this you can see on this figure. This figure is called a wetting envelope and shows in which area a certain liquid will wet the plastics, and that plastic will not be able to adhere air bubbles any longer. It has to be said that complex waste streams are more complex, and that future research had to be focused on the presence of inks and additives, which has a direct influence on the suppression rate of the plastics. And also shape is an important factor to be covered in future research. Also on an industrial scale, we did some tests, and therefore we hired a centrifugal decanter. With this machine, we were able to separate the heavy and light fraction of both waste streams in like two dry fractions, one heavy one and one light one. The plastics of Vanheede and OES are showing promising flotating solids, and those light fractions can be recycled at Govaerts. The principle of the sort decanter is based on density, but here the gravity force is partly removed and replaced by high acting centrifugal forces, and therefore the separation is much faster than conventional zinc float setups. Then the light fraction of the Vanheede stream showed a good composition and has a high polyolefin content. And after separation with the centrifugal decanter, most of the heavy polymers were removed. And then the stream was processed on a lab scale, and the properties were determined. And they showed good properties. But the problem is still that a large fraction of wood is available in the stream, and there is also still a presence of bad odor. Also has to be said that the machine is prone to blockage for some certain waste streams. And now I will give the floor to Martijn.
Thank you, Ruben. Hi everyone, my name is Martijn, and I will now present you the results we have achieved within the PROFIT project to improve the pre-treatment of plastic waste. And I will start with our research to the deodorization of plastic waste. So for this, we first developed a method that is able to quantify odor removal in plastic waste recycling processes. To this, we have compared 3 different sampling techniques. First of all, SPME. Our second technique was activated charcoal in combination with solvent desorption, and the third technique was Tenax tubes in combination with thermal desorption. With those 3 different sampling techniques, we were able to identify 73 different odorous constituents that were present on a post-consumer plastic waste stream. And we have categorized those 73 odorous constituents in different chemical classes, such as terpenes, sulfurous components, and oxygenated components. Comparing those 3 different techniques, we saw that, for instance, SPME showed quite high applicability, but that this technique is not so good to achieve repeatable results. But on the other hand, again, with SPME, it is quite easy to identify the components. The second technique that we tested was solvent desorption, and also this technique is widely applicable. And moreover, this technique shows a good response for the highly volatile components. But for this technique, of course, a solvent is needed, which is, again, a disadvantage. For the thermal desorption method, no solvent is needed, and a quite good response for the high volatile components was achieved. But the disadvantage here is that it was less sensitive for the high molecular weight components. We have applied those 3 different sampling techniques in a case study where we monitored the potential odor-causing components through a recycling chain. And as you can see on the figure on this slide, we identified quite a lot of odor components on the dirty films, as you can see on your left-hand side, and we have categorized them in function of their boiling point and their octanol water partition coefficient. And this last coefficient is a value for the polarity of those components. After washing, we saw that most of the odor components were reduced in intensity, which is, of course, because they were washed. But also what we saw is that the more polar components were more removed, since their color is more dark, than the more apolar components. And this can be explained by the fact that we used water as a washing medium. Then, after the regranulation step, we see that certain components are present again, and even in a higher concentration than the initial concentration, as you can see on the slide where the concentration or where the components are visualized in red. So the main conclusions of this slide is that apolar and high boiling components are still present after the washing step, and secondly, that after extrusion, most of the components are again detected, and sometimes even in a higher concentration. Then our next step of our research was to investigate more fundamentally the deodorization of plastic waste. To this, we have first selected 19 odorous components that have a varying boiling point, octanol water partition coefficient, and molecular weight. And we have applied 5 different treatments, namely water, caustic soda, a combination of caustic and a detergent, only a detergent solution in water, and a solvent. And we have performed our analysis at 3 different temperatures, namely 25 degrees Celsius, 45 degrees Celsius, and 65 degrees Celsius. As a next step, we have then linked the experimentally obtained results to a kinetic and isotherm model. And here we saw that from all the models that we tested, the Fritz-Schlunder isothermal model in combination with the reversible first-order kinetic model gave the best fit. When we look at the results, we see that sodium hydroxide, so caustic soda, was not so efficient to remove odorous constituents, even less efficient than water, actually. By adding a detergent, in this case CETAP, the removal efficiency was seriously increased. And the best removal efficiency we obtained by applying a solvent, in this case ethyl acetate. Another thing that we saw is that the higher the temperature, the better the deodorization. So 65 degrees Celsius gave better results than, for instance, 25 degrees Celsius. And these things can be explained by considering the deodorization process as a solid-liquid extraction process. And typically, such a solid-liquid extraction process is influenced by the polarity of the extraction medium and by the temperature, what we also saw for deodorization. Then, as a next step, we have performed some osmo simulations to investigate a bit more in depth some industrially relevant parameters, such as solid-liquid ratio, residence time, and recirculation rate. And what we saw here is that the solid-liquid ratio was quite an important factor, since the higher the solid-liquid ratio, the lower the efficiency that we obtained. On the other hand, the residence time is not very important, let's say, because what we saw is that an equilibrium was already achieved after 2 minutes. But our third factor, the recirculation rate, again, is a quite important factor and maybe even one of the main hurdles to increase the deodorization efficiency, because what we saw is that applying a recirculation rate of more than 60%, as you can see in the yellow circle, significantly drops the deodorization efficiency. Knowing this and taking into account that currently most companies apply a circulation rate of more than 90%, this explains, of course, the relatively low deodorization efficiencies that are currently achieved. And if you think back to our kinetic model, which was a reversible first-order kinetic model, this can explain our results, because what we see is that not only desorption takes place, but on the same time also adsorption from the washing medium to the plastics can take place. Now I will shortly introduce our research to the de-inking and delamination of plastic waste. So what we have done here is we have tested different mediums and at different conditions, and we have always optimized our procedure till at the end became a method that was able to remove all the inks and the adhesives that are present on plastic films. So you can see here some results that we have obtained with, on your right-hand side, a completely de-inked plastic film stream. As a next step, we have optimized this method, and for this we first developed a method to quantify both the de-inking efficiency and the delamination efficiency. The method to quantify the de-inking efficiency is based on color mapping, and the method for the delamination efficiency is based on an FTIR analysis. As such, we were able to optimize our process in terms of solid-liquid ratio, shear rate, temperature, and so on. We have filed a patent for this method, so we can, on this moment, not fully disclose our method yet, but we can say that we have tested our method on a real waste stream, as you can see on the picture on this slide. And this gave very good results. As you can see, all the printed films were de-inked after our procedure. We are currently doing research to upscale this method, so in the future this might be applied by industry. So we will now see two videos, one of my colleague Ruben, who you already saw, and one of my colleague Sibel Ugdeler. Ruben will first show the film blowing process, and then Sibel will show you the de-inking process in the lab.
Plastics coming from packaging waste pose a major recycling problem. Creating closed-loop systems for these valuable materials is difficult. Post-consumer waste streams, like the ones considered in the Matter and Profit project, contain a lot of plastic and non-polymeric contaminants, like there are metals, paper, and wood. In this video, we are showing the film blow process. This polymer processing technique is very delicate, and the presence of these contaminants will cause problems during processing. In this video, you can also see that recyclates often have a dark color. Therefore, research on de-inking and delamination and on the separation of these contaminants is crucial.
Hi, my name is Sibel Ugdeler. I'm a PhD student at ICP Research Group at Ghent University. Now I will demonstrate some experiments on removal of different types of inks from plastic films. Here we have 4 different samples. First two ones are printed with solvent-based inks, the next one is with water-based ink, and the last one is printed with UV-based ink. After we cut them in different shapes to recognize easier, we bring them in contact with the de-inking medium. Normally, UV-based cross-link inks are one of the hardest inks to remove. But as you see here, with our developed de-inking procedure, we are able to remove all different types of inks successfully and in a short time frame. As you can see here, in case of multi-layers, first we delaminate the sample before the de-inking step.
A third area within the research of Profit was on the recycling quality of waste plastics. Mixed plastics, when remelted, are forming a phase-separated structure, and therefore they often have lower mechanical properties. In order to map the influence of different polymer combinations, we produced blend series. And of these blend series, the different mechanical properties were determined. Also, the morphology and crystallinity of these polymer systems were considered. The table on the slides show the theoretically compatibility between the different polymer pairs. And with this research, we gained insight in the occurring and changing deformation mechanisms of these blend systems. Next, we set out the properties and function of the contaminating polymer. And based on general trends, we were able to devise two decision schemes. One is focusing on the tensile strength and on the elastic modulus. Another one is on impact strength and elongation at break. This is such a scheme. And this scheme should give a clear image of what the recycling potential is of a plastic stream. A little example. If you have an LDPE contaminated with PP, then this will lead, the scheme will tell us that this will lead to these properties. Of course, future research will focus on making better those predictions of the mechanical properties by gaining insight in mixes of different grades of polymers and also on the influence of non-polymeric contaminants. In the Profit project, we also reflected on the total quality and the features that are important for the total quality of waste plastics. And therefore, we focused also on optical properties, content of harmful substances, and processability. And in next research, we will try to combine these different features into a single recycling quality factor, ranging from 0 to 1. And this will have, we want to create a quick vision of a waste stream's quality based on this recycling quality factor and on the pretreatments required to gain new recycled waste products. And now we will see another video by Vanheede that will show the reflections of Vanheede on the Profit project.
Vanheede Environment Group is a fully integrated waste management company, and our aim is to be active in the circular plastics economy. In Profit case, we can collect and sort the plastics in our automatic sorting plant, and the final recycling step is also done in-house. Our collaboration within Profit gives us the opportunity to test several plastic waste streams and to meet potential partners in the whole supply chain. This is useful for establishing a circular business model for plastics. We had a very good support from Professor Steven de Meester and his Ghent University team. They provide support for the academic and the very practical issues.
There we have it. That was quite condensed and at a quite high pace, a lot of the results from the Profit project. As you can see, a lot of scientific and technical advances were made that help us understand better what these plastics are, what their challenges are, and how we can advance towards solving them. But we're also not quite there yet. So this type of value chain cooperation remains very important also towards future projects to keep doing exactly that and to keep advancing us to full circular plastics. With that, we can wrap up the first part, which was the presentation of the PROFIT project results. And we are now moving on to the second project, which is the MATTER project. MATTER handled the streams coming from the P+MD bag and was as a project coordinated by the company Indaver. That is why, to present to you these results, I would like to invite Mr. Erik Moerman from Indaver.
Thank you, Kim. The MATTER project it has been a very interesting journey, let's say. If I try to remember, I think it was May 2017 that the first idea came on the table. And in 2-3 months' time, basically, we found all the necessary parties to write this project application. And the partners, they are numerous. On the one hand, it's academic partners like University of Ghent, University of Antwerp, but also industrial partners like Borealis, Bulk ID, EcoA, and also the company I'm working for, Indaver. With these partners, we really brought together the expertise that we needed to bring this project to a real success. And in the slides that will come after my slides, you will see what the successes are. I think it's also important to mention that next to these partners, there's also some stakeholders that we involved, let's say experts in the recycling of plastics, which are OVAM, Plarebel, and also Fost Plus. And Fost Plus also will be part of the panel discussion later on. Also their expertise was very welcome. We brought all these partners together, and that was definitely with the help of Catalisti, that helped us to write the project, looked for the right expertises and so on, so that we are very grateful that Catalisti was helping us with this project. And at the end, I think we need to thank also Vlaio, because the money at the end that we used to go through the different steps of the project came from the Flemish government through the body Vlaio. The base of the project, where this started, because there was this new initiative to extend the blue bag, as we know it in Belgium, where we collect already since many years the different packaging waste from the households. And at a certain moment it was decided to extend these bags to new fractions, and mainly fractions of plastic waste, like plastic trays, plastic pots, plastic foils. And with this, the amount of packaging waste that was collected extra increased with 80 to 100,000 tons per year in Belgium. Now, what was the goal of the project? At the end, we were able to develop a set of criteria to support actually the decision towards the optimal plastic waste management scheme. There's a lot of nice words. What is a good waste management scheme, or what is a complete waste management scheme? That starts with really knowing the waste. And Martin, who will following after me, he will explain a little bit more on that. But you have collection, you have sorting, you have pre-treatment. And I think what is quite unique in this project, that we also make the comparisons between the mechanical recycling, which is a technology that already exists for many, many years. But also we included the thermochemical recycling. And we compared both, and the comparisons was made based on two evaluation tools, which was on the one hand the technical economical analysis, and on the other hand the LCA. And I think before jumping to the final conclusion, maybe a small thing I can say already, we really see there is a big gain to make in terms of CO2 avoidance by recycling these extra plastics. So I would like to give the words now to Martin.
Thank you, Erik. Hi again. So I will now present you the first work package of Matter, namely the analysis of the feedstock quantity and quality. So to recycle plastics in high-value applications, it is important to know the composition of the waste, of course. And by the extension of the blue bag, there came some new waste streams on the market that were not fully known yet. And therefore, we decided to first characterize those new waste streams. And for that, we have applied following methodology. So first, we have assigned representative products, as we call them, to each waste stream. A representative product we selected on the sales numbers of the biggest Belgian food retailer. And by this methodology, we were able to cover a more relevant fraction of packaging products that are present in waste. And moreover, by this methodology, we were also able to average out seasonal and geographical variation. Then, after assigning those representative products, we have sampled different of those representative products at the outlet of a sorting plant. And then we started characterizing them in the lab. And this included, among others, the polymer composition, the elemental composition, the moisture and dirt fraction, and so on. Furthermore, we have divided each product that we selected in their separable components. So for instance, a PET tray we have divided into the tray itself, the lid that is present on the tray, and the label that is present on the tray. And we have analyzed each of those different separable components individually. This means that on each component we have applied ATR, FTIR analysis, POM analysis, and DSC analysis to characterize them in terms of polymer composition. And then we have also applied ICP-OES analysis, combustion ion chromatography analysis, and CHNSO analysis to get to know the elemental composition. And here on this slide you can see the polymer composition. So we don't have enough time, of course, to go in really detail, but I will guide you through the main conclusions that we can draw from this figure. So for PET bottles, we see that a relatively pure stream is achieved, but that caps and labels that are present can contaminate this stream, which mainly consists of polyethylene and polypropylene. PET trays are a bit more complex because they are often multi-layer, consisting of polyethylene and polyethylene terephthalate. Also, what we saw is that sometimes there are paper labels present on the PET trays. The PE and PP bottles were relatively pure streams again, but also here labels and caps coming from of having a composition like polyethylene and polypropylene can again contaminate these streams. For the trays, we saw that relatively pure streams were obtained for PP and EPS, but again, labels and liddings can contaminate these streams. For the film stream, we have made a distinguish between the monolayer films and the multilayer films. The monolayer films mostly consisted of polyethylene, but for the multilayer films, we saw that many different polymers were present, among others PET, PE, PP, EVOH, polyamide, and so on. Also, sometimes those multilayer films contain a certain paper label. And this polymer composition is very important for mechanical recycling, because what we see is that if certain polymers are blended together, this can deteriorate the quality of the recyclates that are produced. And this can be explained by the morphology of those blends, which sometimes have like a droplet matrix morphology, which can induce propagation of these cracks and a little brittle behavior. When we take a look at the elemental composition, we see also very interesting results, but maybe these are a bit more interesting and relevant for thermochemical recycling. So what we see here is that, for instance, there was a high difference in terms of oxygen content. For instance, the PET streams, or PET-based streams, they contain a high oxygen content, and oxygen can, for pyrolysis of polyolefin-based waste streams, result in production of certain acids which can corrode the equipment. A second thing that we analyzed were the metals, and here we see that certain waste streams also contain quite high levels of metals. For instance, the polypropylene bottles contain on average 130 ppm of sodium, which can induce coking and the production of charcoal during pyrolysis. A third thing that we saw, that we analyzed, was the chlorine content. And also here we saw quite high values. For instance, the polypropylene trays contain 229 ppm of chlorine, which is much higher than the, let's call it the threshold that is sometimes stated in the literature of 10 ppm. So as a conclusion, I would like to say that both thermochemical recycling and mechanical recycling are still facing certain issues, let's say, or challenges. And I have put a third factor here on this slide, and that's a design for recycling, because often those issues comes from the complex packaging. And so working together within those different factors can really improve recycling. So improving guidelines for packaging design, but also for plastic sorting, pre-treatment, and mechanical and thermochemical recycling is really necessary, tailored on the specific composition of waste towards achieving a more circular economy for plastics. Thank you, and I will now give the floor to Professor Steven de Meester, who will introduce the sorting model of Ghent University.
Okay, thank you, Martijn. So indeed, after knowing the composition of waste, we go through the recycling chain. And the first step of the recycling chain of plastic typically is the sorting. So sorting, it's not an easy process. It's typically these big halls where there's over 80 equipments, and it's very complicated, a complex mix coming in, a whole bunch of processes over these conveyors going at high speed. So it's difficult to, we had some brainstorms, what should we really do about this? What can we really do as a method project to, well, make a step ahead in this kind of processes? So we could do some separate tests. There are nice testing centra in Germany, in France, in the Netherlands. So there are test centra where we could send big bags to do test, and that is absolutely needed, and what we also sometimes do. But in this case, we thought, and in matter, in fact, we want to develop scenarios to compare mechanical and thermochemical recycling, and we want to make scenarios. So we want to have something more modular compared to sending a big bag, one big bag of waste, which is difficult to take in a representative way. So we wanted to have a model to do this in a more flexible way. So if you look to a sorting plant, as I mentioned, it's very complicated, but the amount of equipment is high, but the types of equipment is not so high. So in general, you can say there are NIR separators, there are ballistic separators, there are eddy currents, there are drum sieves, and a few others. So the amount of, or the different types of equipment is only around 7 or 8 or so. So we thought if we know this process a bit better, then maybe we can develop a flexible model to predict how waste flows through these sorting plants. And at that point in time, yeah, that was a big job, but we had a good thesis student. Thesis students, the free labor of universities, in case they are good, of course. Sometimes they are also the opposite. But if you have a good thesis student, of course, you can make a nice progress. And in this case, we were lucky to have someone like that. And we just said, let's start this and see where we end up. And what we did was we looked to, as a really system view to these sorting plants, and we see that every process has a certain separation efficiency, which we call a split factor. And this split factor determines if you have 100 PET bottles going in a process, in a NIR PET, how much of these PET bottles end in the positive direction. But also, if there is still PS on that conveyor, how much of the PS is mis-sorted on a PET NIR, and so on. So we have positive and negative sorting. So if we would be able to understand these split factors, so the efficiencies, we would be able to model the sorting plant as a whole, depending on the input composition. So that was a big job, good for a thesis student, as I mentioned, where we looked to machine specifications, experimental data that we had, which is quite scarce to have really on a polymer level. But we looked everything we had, also a bit like in drum sieve, you can look to the shape and the size of equipment of the products that go through. Also some expert judgment. So every data point we were able to collect, we used in our split factor matrix. And in the end, we put this in a nice mathematical formula. So as many PhD students know, if you work on recycling in Excel, Excel doesn't like loops, and then it crashes. So if you want to avoid loops, in this case, of course, sorting plants have a lot of loops. So we used an elegant matrix calculation to oppose this problem, I would say. So what we then did, we made this big what we call a split factor table, which is basically saying which types of products, by the way, the same products as those that we analyzed in work package 1. So in the number of rows, there are the types of products, and in the columns, there are the type of equipment that are present in a sorting model. So we developed this big split factor matrix. This is really the heart of the model. Then based on the matrix calculations, we can somehow model any type of sorting plant, so we can flexibly adjust the type of and the design of a sorting plant, and then the model gives you the output bales that come out of this. And for these bales, we define the recovery, which is the amount of, if you put 100 bottles inside and at the entrance of the sorting plant, how much bottles, PET bottles, do you get out of in the PET bales. And then the grade is, in the PET bale, how much other products, how much PET is really in there. So it's a purity level, how much PET is really in there, and how much contamination is in there. So that's what you finally, the yield and recovery, or grade and recovery, is what you get out of that model. So we validated the model. That's, of course, as any model, it's important to validate. And that you see on the top left of the slide, on the orange bars, we validated this on the P+MD. As in Belgium, the P+MD was actually running already, so we had experimental data to compare our model results with. And in fact, we were pleasantly surprised that we had quite a good comparison between the model results and the experimental data. So that gave us confidence to say that maybe this modeling approach is not so bad. So we went on and tried to predict the P+MD scenario. At that point, was around 1 year ago or 2 years ago. We didn't have that much data, especially on the new sorting plants that are, as we speak, being built. So we didn't have that data yet, but we were able to see if you get the expected P+MD input composition and you get the expected designs of sorting plants, what recoveries and yields will we achieve? And we were pleasantly surprised to see that the sorting plants that are about to be built will probably, according to our modeling results, get the specifications that are required in most of the categories. So also these that was a bit of danger before going from P+MD to P+MD, that nice fractions like PET and HDPE bottles and so on, that they would be more contaminated. But in fact, we see that from our results that this is quite okay. Even after extending, making the bag more complex, these nice new sorting plants, which are a bit more complex or quite more complex compared to the P+MD system, they are still able to have high purities out of the PET and HDPE bottles. So that was very nice to see. The film fraction is a bit of a difficult one, because there you have the PE films and other films, and you have to play a bit, and the sorting plant can play between how much PE film and purity can I really have there compared to the other film fraction. So that is, and also we face a bit of difficulties to define, in fact, what is a PE film and what is other film, because many films contain some PE, and where do you actually put the boundary between these two? So the film stream is quite a complicated one. We also did some scenarios, because the film stream is one of the more difficult ones, to make loops on this internal loops in the sorting center to predict how these loops affect the purity and recovery of the film fraction. So this is to show that you can predict new design, you can use new designs and other products through the sorting plant in the model and see how they come out. But you can also change designs in the sorting plant and see how that affects the recoveries and the yields. And then, in my opinion, the true power of what we did, if I'm allowed to say so, is in the fact that we can combine work package 1 and work package 2. So work package 1 has a very detailed compositional analysis, and where we have these products well defined, the caps, the bottles, the liddings, the labels. We know how much chlorine is in a label. We know how much metal is in a cap, so we have a very good understanding of the composition. And if we combine this through the model, we are actually able to say, without going into the details of what is currently on the slide, we are able to say, so how much caps are there? Also, what I didn't stress too much yet is the LAMD, so the level of attached moisture and dirt. So how much of that moisture and dirt do we expect in every bale? How much metals come through mis-sorting in a certain HDPE bale? Or how do films distribute throughout a supply chain, throughout the sorting plant, and which fractions do they also end up with? And with that also, how many labels on these films end up in these streams? So the positive and negative sorting we can predict in a more deeper level, is my opinion, compare how this affects the total metal concentrations or polymeric compositions and so on of these different bales that you expect in a system. So summarizing, we have developed a model where we where you can give in your input stream, where you can puzzle your flow sheet of the sorting plant together. And also we can combine this with this elemental and metal and polymeric compositional analysis and then predict how these bales come out, which is both relevant for mechanical recycling and for thermochemical recycling. And this is important feedback for the later work packages. So after this sorting, we would go to washing. So we have, during the profit presentation already, these bales go to washing. So during the profit presentation, we have spoken a bit already on these washing techniques. So I will not do this here in this presentation, but I will give the word to ECO, who are since many years already, since most of us were talking about recycling, since many years, ECO is really active in recycling and doing it on the floor, recycling tonnages of plastic. So in that sense, they are a really important role, as they are not here due to the COVID, of course, but they are not here today, but I want to stress how important they were for the project, and therefore I would like to give the word to ECO, who recorded the video for us.
At ECO, we are happy to take part in the Matters project. Working in co-creation together with other organizations who share the same values results in remarkable synergies. All organizations contributing to the project are working towards the same goal, improving the recycling of mixed post-consumer plastics in order to create a sustainable future. This is also what we do at ECO every day, but in co-creation with others, this is more effective and the impact is more extensive. We experienced that the combination of the academic knowledge and research in combination with industrial experience brings us further together than alone. We want to thank all the partners for their cooperation. Sincerely, thank you very much.
The Matter project wants to make a trade-off between mechanical recycling and thermochemical recycling. In order to do this, we focus on different sorted out fractions of the P+MD system. And now I will explain the results obtained for the mechanical recycling for different streams. The first stream is a PP rigid fraction. This waste stream consists of about 97% PP and only 3% AGPE contamination. We started from the PP waste, but also from a fraction obtained after industrially melt filtering by ECO. The lab scale testing showed that the PP stream had good processing and mechanical properties, and no bad odor was remarked. Then, in cooperation with the manufacturer Ragaert, we tried to process planters, and those are like injection molded products with a wall thickness of 4 to 5 millimeters. And to conclude, we can say that the PP rigid stream was well mechanically recycled. A second stream on which we tried mechanically recycling was a PS rigid stream. This PS waste was shredded, washed, and then extruded into sheets for thermoforming. On lab scale, it became clear that other polymers were contaminating the waste stream. And those rubber-like components caused rupture in the polymer sheets during thermoforming and during extrusion. So the lab scale testing failed for the thermoforming of the PS sheets material. And two solutions can be offered to remove those contaminants. The first one is a melt filtration on an industrial scale, and the second one is an extravisual sorting step during the sorting process. Then a third fraction that we subjected a mechanical recycling test to is a PE film fraction. We wanted to again make film material from this waste fraction. The first goal was to scale the properties of the blown PE film waste against virgin LDPE and LLDPE blown grade polymers, and also against commercially available EcoPlus grades. A second goal was the processing of a de-inked fraction of the PE film fraction. We have to say that the PE film waste could not be processed into film again as such. and therefore it was decided to blend the PE film waste with film blown grade LDPE and LLDPE. If you look at LDPE as a reference, we see that the blends with polyethylene recyclate have a lower MFI, but were well processable on lab scale. Also a higher stiffness, but reduced strength and elongation at break were remarked. And this can be caused by the contaminants that are present in this waste stream. If you look at the visual aspects of the PE film that we produced, then we still see that the stream consists, or that the film consists specks. If we then look at the 50 and 70% LLDPE blends, then we see because the LLDPE has a higher properties, the gap to be bridged by the PE recyclate is more difficult. But we can again say that the processing on lab scale was again good. But for the visual aspects are still lacking, and this is due to uneven films, a somewhat darker color, and the presence of specks. So we can conclude that the PE films could not be processed into the existing recycled PE film quality. But we can consider blending with LLDPE, and so in this way we can achieve a technical quality comparable to an LDPE polymer. Of course, it has to be verified whether this is cost effective, and also the processability to uniform film on a larger industrial scale is important. For the de-inking step, we did a trial on a de-inked sample to see what's the positive influence on this processing. The film blow processing seems to be better, but it still has, it still contained a lot of contaminants that are not melting, and these non-melting contaminants cause rupture of the PE films. And we have to notice that an extra sink float step could be a possible solution to remove those higher melting polymers. And now we will go over to an extra video in which Borealis give his reflections on the Matter project.
We have as Borealis highly valued the cooperation in the Matter project. The topic of assessing how mechanical and thermochemical recycling of plastics go hand in hand is also at the core of the Borealis' own investigations. And the project consortium we felt being a strong one with a balanced mix of academic and industry partners. And last but not least, also the interaction of the project with the societal partners, Fost Plus, Plarebel and OVAM was particularly interesting. For me personally, a highlight was surely in the summer of 2019, the joint visit and the technical discussions with Professor Ragaert and Professor De Meester at the Borealis Innovation Center in Linz and at the Borealis Ecoplast recycling plant in Wilden, both in Austria. And the insights of this have also been captured in the Matter project.
In the next video presentation, Moerman from the LCT of University Ghent will explain the results obtained on thermochemical recycling.
Hello, my name is Moerman Kusenberg, and I am now going to present the results of work package 4, thermochemical recycling. I will begin with an overview, thermochemical recycling of plastic waste. We can start with plastic waste from, for instance, the P+MD bag, which goes into a pyrolysis reactor, which is used to crack the plastic waste to produce a pyrolysis oil, which can be seen here on top from a real waste, so it's quite dark and viscous. This feedstock can then be used as a feedstock for petrochemical industry, such as a steam cracker, which then produces ethylene and propylene and also other chemicals such as butadiene and aromatics, which then can be used to close the material loop while producing new plastics. The outline of this talk. First, I will begin with pyrolysis experiments of mixed plastic waste performed at the Laboratory for Chemical Technology at Ghent University. Then I will talk about the analysis of these plastic waste pyrolysis products, especially the liquid products, using comprehensive two-dimensional gas chromatography and also ICP-OES. And then I will talk about steam cracking experiments of crude plastic waste pyrolysis oils, which were performed as a proof of concept in order to see if we actually can crack plastic waste pyrolysis oils with no further treatment. I will finish the talk with conclusion and an outlook. Okay, post-consumer plastic waste pyrolysis at our lab. We have a unit such as this one here, as you can see in this scheme. We use post-consumer plastic waste. We put it in a hopper, which is then in an extruder melted and fed to this reactor. In the reactor, the actual cracking takes place. And then the products will leave the reactor at the top in vapor form and will be then condensed in a dedicated condensation section to then draw a liquid product, which looks like this. This liquid product can be used or can be then injected onto our GCXGC-FID setups, yielding a chromatogram like this one. In this chromatogram, which is just an example, can already be seen how many compounds we actually have. So we have a multitude of different compounds, of different compound families, such as paraffins and olefins and naphthalene and aromatics. But we have also within these families a huge amount of different compounds. The used feedstocks in this project were two MPO, so two mixed polyolefin feedstocks, MPO flex and MPO rigid, one PP waste feedstock and one PE films feedstock. Okay, now the analysis results, GCXGC-FID, of the four respective waste feedstocks. We have 4 pie charts according to the 4 different waste feedstocks. We have the color schemes: blue paraffins, orange olefins, yellow aromatics, and gray naphthenes. It can be seen right away that all 4 waste streams or plastic waste pyrolysis samples have quite wide carbon number ranges, so from C5 to C51 for the MPO flex, but also for the others it goes almost up to C50. And we can see right away that all of them have a quite high olefin concentration. So the orange parts of the pie charts are quite large for all of them. What can be seen, however, is that the PE-rich sample, so PE film, which mainly consists of polyethylene, yields higher amounts of paraffins, while the PP-rich waste PP waste pyrolysate yields a significant amount of olefins. So this almost entirely consists of olefins. Concluding, it can be said that the olefin concentrations of all 4 samples are still far too high for steam cracking. So this would mean that we expect a lot of fouling and coking issues in a steam cracker when cracking these fractions crude without further treatment. Now, the metal analysis. So what we want to know is the contaminant levels, because the contaminants in plastic waste pyrolysis oils are crucial. They're one of the key aspects, or if not the key aspect, to assess the feasibility of steam cracking these feedstocks. What has been seen is that the metal contaminants are not spread evenly across the pyrolysis products, which means that most of the metals end up in the solid residue of the pyrolysis, which can be seen here in this pie chart. The blue part is the solid pyrolysis residue, the metal content of the solid pyrolysis residue, and the orange one is the crude pyrolysates and the metal content. It can be seen that most of the metals, almost 99% of the metals, end up in the solid pyrolysis residue, i.e. coke, which is remaining in the pyrolysis reactor, while only 1% ends up in the crude pyrolysate. The question now is that already solving the problem? So have we already lowered the contaminants in our liquid pyrolysis oils so far or far enough to use them as a steam cracking feedstock? Unfortunately not. So the metal content of crude pyrolysis oils is still far too high for steam cracking, which leads to the conclusion that these feedstocks will have massive issues in a steam cracker. This raises the possibility of distillation of the crudes as a further mean to reduce the metal contents, while, for instance, we can remove most of the metals with heavier distillative cuts, and the light cuts which we need for steam cracking are then essentially metal free, but this is to be examined in the future. As I said in the beginning, we performed steam cracking experiments of pyrolysis oils to assess the potential of the crude oils as steam cracking feedstock, so basically as a proof of concept. We used a setup like this one, which is a bench scale steam cracking setup at the LCT in Ghent. We cracked an MPO pure with a coil outer temperature of 850 degrees C. We used the same conditions to crack a naphtha reference feedstock. So this is a fossil naphtha which is used in industry. it can be seen right away as a first conclusion here that the light olefins, so ethylene and propylene yields are quite high compared to the naphtha. So we're in the same ballpark as with the naphtha range, which is very good information already. However, it can be seen here that the total C4-, so total light products, are a bit lower than for the naphtha reference. So that means we are getting more heavy products, which can be seen here in the pyrolysis fuel oil range is C10+. We reach almost 9% of these products with our MPO pure, while we get less than 1% with the naphtha reference. And this is mainly due to secondary reactions, which are basically due to our high olefin content in the feedstock. And that means that these feeds need pretreatment. So it's not feasible to use these feedstocks pure in a steam cracker because we have a lot of fouling and coking issues expected for these feedstocks. So in order to reduce these tendencies, we need to pretreat these feedstocks. As a conclusion, it was said that the plastic waste composition has a huge impact on the actual molecular composition of the oils. So that was seen with PP-rich pyrolysates, which contain a lot of olefins, while PE-rich pyrolysates contain less olefins and more paraffins. The contaminant levels in pyrolysis products, it was seen that around 99% of the metals end up in the solid coke. However, the remaining concentrations are still quite high, and that means that we need to further lower these metal amounts in our liquid pyrolysates. And as I said already, distillation can be an effective and rather simple treatment step, while just removing the very heavy cuts, which most likely contain most of the metals. The proof of concept experiments. So we steam cracked crude plastic waste pyrolysates, and we have seen that the light olefin yields are quite nice. They're in a range with fossil and naphtha, which is very good. However, we also see a lot of heavy products, which are mainly due to the high olefin content, which lead to secondary reactions, which then lead ultimately to fouling and coking potential. So this has been shown that we really need to pre-treat these feedstocks in order to make them more feasible for steam cracking. Potential pre-treatment was already mentioned with distillation to remove contaminants, but also hydrotreatment is a very potent technique to actually reduce unsaturated hydrocarbons and heteroatoms. Thus, using hydrotreatment, we can most likely produce a very, very nice feedstock based on plastic waste, which is comparable to fossil naphtha. Thank you very much.
Hi again. We will now continue with work package 5 of Matter, which is called Sustainable Market. And this work package will be presented by Pieter Bille, Macarena Larrain, and Sophie Huisveld. And this will be again a video presentation.
Pieter Bille from the University of Antwerp, and together with colleagues from the University of Ghent and with input from many different project partners, we studied how recycling innovations could lead to a more sustainable market. In a nutshell, we considered challenging fractions from the P+ sorting facilities output, such as PP bottles and trays, PS trays, PE foils, MPO rigids, and other foils, as candidates for either mechanical recycling or thermochemical recycling. Via dedicated mass and energy balances, we performed a techno-economic assessment as well as a life cycle assessment. Ultimately, we produced a tool to balance the economic and environmental effects using different indicators in support of decision-making for different stakeholders.
In the LCA, we calculated the net environmental impact per ton of waste. This was done for several impacts such as resource consumption and global warming. Following the presented equation, first, the burdens presented in red are calculated. These are the adverse impacts of the sorting, pre-treatment and recycling processes. Second, the credits presented in green are calculated to account for the benefits from recycled products. These equal the avoided impacts of virgin material production. In case of 1-to-1 substitution, we assume that 1 kilogram of recycled material substitutes 1 kilogram of virgin material. Third, the net impact is calculated by subtracting the credits from the burdens. The more negative the value, the better. However, to account for the potential different technical quality between the mechanically recycled materials and their virgin alternatives, the credits are multiplied with the quality factor based on mechanical properties. The quality factor is a value between 0 and 1. Additionally, when comparing both recycling options, an important difference is that the current food contact regulations do not allow to use mechanically recycled materials except PET in direct food contact applications. To account for this, we multiply the credits also with a market factor, representing the potential market share, thus excluding the food packaging market in case of mechanical recycling. The results for global warming show that both thermochemical and mechanical recycling are favorable over incineration, the benchmark presented in gray bars. Comparing both recycling options, the net impacts presented in dark blue bars are from best to worst for S, PP, PE films, and MPO. Key aspects are first, the contamination of the waste fraction, the lower the better the result. Second, mechanical recycling generally receives higher credits as its products can directly be used in manufacturing, while the thermochemically recycled products such as naphtha cannot and should undergo still cracking and polymerization. However, and third, accounting for technical quality and potential market share substantially reduces the credits for mechanical recycling and brings the net impacts of both recycling options closer together. Only in the case of PS, the net impact of thermochemical recycling becomes more beneficial compared to mechanical recycling. The approach with quality and market factors can be further investigated in terms of uncertainty and updated when mechanically recycled products could be used in the future in direct food contact applications.
Hello, I'm Macarena Larraín and I will talk about the techno-economic assessment and the decision model. For the TEA, we calculated the net present value per ton of plastic waste, using as a basis the same mass and energy balances as the LCA, and accounting for the revenues of the recycled products, the cost of revenues of the plastic waste, the operational expenditures, and the capital expenditures. With the sensitivity analyses, we've studied which are the variables that have a larger influence on the results. In this tornado chart, we can see that the most important variables are the product price followed by the product yield. The exact values of these and other important variables are hard to know. So we propagated these uncertainties to get the probability distributions of the NPV. In these graphs, the shaded area represents the probability of a positive NPV. We can see that in all cases, the shaded area is less than half of the total area, implying that the likelihood of having a profitable business case is smaller than 50% for all plastic fractions. For chemical recycling that requires large investments, the discount rate and the capex are the variables with the biggest influence. Product prices, which are assumed to be coupled directly to oil prices, are very important as well. Results show a likely positive outcome for P films and PS trays, yet a more challenging situation for PP bottles and trays, MPO rigids, and other films. To estimate product prices, we took projections of oil prices over a longer period of time. We included a scenario where, due to a lower demand, oil prices would decrease in the future. The different shades of blue and green represent the uncertainties of these estimations. Nevertheless, the COVID crisis has shown that shocks can make prices fall outside of the uncertainty ranges we accounted for. Additionally, new policies regarding, for instance, mandatory recycled content would change prices in the market. To analyze these or other potential scenarios, this framework that we developed to analyze the economic performance would need to be updated. Let's move on now to the decision model that was developed with the software Analytica. In the blue area, we have the inputs for the TEA. In the red area, we have the inputs for the LCA. Then in this big yellow area, we get the results. In the input area, you can change some preset default values. If a user wants to, for example, analyze the situation in a different country, would have to change the tax rate and, for example, the waste price, and insert the values for the country to be analyzed. These spider charts show the net present value, the internal rate of return, the scene, and the global warming as performance indicator. To update them after changing the input parameters, you click on the blue bag. Then on these buttons of the right, you get detailed results of this and other indicators such as energy consumption or social net present value. That includes the cost of carbon emissions. By selecting over here Monte Carlo, you get the probability distributions of the results. Finally, the model shows the flow diagrams of the different recycling processes. Following on this presentation, you can see a short video of Udo Kresovic on behalf of Indaver, exemplifying the value of the Matter project for Indaver. Thank you very much.
We will now go over to two videos. In the first video, as Macarena already said, Udo Kresovic will draw some conclusions from the Matter project on behalf of Indaver. In the second video, Marvin Kuzenberg will show the setup they use at LCT to perform their pyrolysis analysis and experiments.
Indaver is grateful being a member of a broad consortium of academic and industrial partners assembled together in the course of the Matter project. In specific, we would like to thank Professor Domestic, Professor Vanheede, Professor Ragaert for all the works and efforts made in the course of the project. In the sessions organized in the course of the Matter project, we got the opportunity to learn better waste plastics landscape in Belgium and to compare different recycling routes, namely mechanical and chemical recycling. Life cycle analysis performed during the project showed clear benefits of using chemical recycling in reducing carbon footprint of plastics supply chain. At the end, we would like to thank all, and we are hoping to bring chemical recycling to maturity in the course of our plastics chemical development.
Okay, hello, my name is Marvin. I'm working on work package 4 of the Matter project. It's called thermochemical recycling. We use this unit mostly for our experiments. Here you have on the right side in yellow the extruder part, which is used for feeding and melting the plastic waste. We have the plastic waste here in this glass. It's pelletized, so we can feed it nicely to the hopper. Then it's melted and fed to the reactor, which can be operated at various conditions, so the different temperature pressure profiles. Then the plastic waste is pyrolyzed in the reactor. It leaves the reactor on the top in vapor form, then it's condensed in the condenser here, and then it can be drawn at the bottom in liquid form, and then you get a nice product like this. The products can be used for all kinds of petrochemical processes, for instance steam cracking to produce light olefins that can then be used to produce new plastics.
Thank you very much, Marvin. That concludes what we have to show you on behalf of the Matter project. All that is left now to us is to wrap that up. So as you can see, the Matter project, just like Profit, was really a value chain cooperation. We work together across that entire value chain, and it is only by feeding back information between the different blocks and also between the sorting qualities, the chemical, the mechanical recycling, that we will be able to make this real progress in what we could do with the P+MD streams. So I really think that I can say that we made a contribution there to the state of industry. Well, we now come to the more interactive part of this afternoon, and we can introduce the panel for today's panel discussion. We have quite a diverse panel, but all members do have a very strong background in engineering. As a first panel member, I would like to introduce Professor Steven de Meester, who is a professor in circular process engineering here at Ghent University and has been the academic lead on both of the projects presented today. Our second panel member is Jan van Havenberg, the managing director of Catalisti, which is the Flemish spearhead cluster for chemical and the plastics industry. Our third panel member of today is Mr. Erik Moerman, who is the manager business development at Indaver and who has been guiding the company to contribute substantially to the circular economy since 1997. He was also the industrial lead on the Matter project. As a fourth member, we have Mr. Nico Kimpe, which you have seen earlier already. He is the program responsible recyclable materials at Vanheede Environment Group. He has a whopping 13 years of experience in waste management, and he was the industrial project lead on the Profit project. And the final member of today's panel is Mr. Philippe Gendebien, who is the Business Development Cluster Manager at Fost Plus, and he is responsible for the transition to P+MD in Flanders, and as such has been a very important project partner in the Matter project. Before we start the panel discussion proper, there's two aspects which I need to introduce to you. There's two ways for you to weigh in on today's discussion. First of all, there's the polls. When I ask some questions to the panel members, sometimes I will ask the same question to you in the audience. You will see a poll appearing mid-screen, and you will have some time to answer this poll and to give your opinion. We will then take those results a little bit later and present them to our panel for their analysis. The second option which you have to contribute today is to ask your own questions. If you have specific questions that you would like to address to either the entire panel or to one specific member, you can just add them in the chat box section, which you should be seeing on the right side of your screen. You can put there your questions. We may not be able to pick them up immediately. It will be as we go along or towards the end. And if there are questions which turn out to be not picked up at all because we don't have enough time, then we will make an effort to get back to you after the event. Okay, let's kick it off. Gentlemen, we've already spoken today about the P+MD. Belgium is transitioning from PMD to P+MD, in which consumers may now put all post-consumer packaging waste. I would like to ask, what are your expectations regarding the effect of this on collection and recycling rates? And Philippe, as Fost Plus is overseeing the transition to this system, what is your opinion on this?
So it's a big challenge and a big advantage to recycle more plastic packaging. The goal is to increase collection from 160,000 tons to 250,000 tons, meaning about 90,000 tons plastic packaging could be recycled thanks to the extension of the blue bag. It's about 8 kilos per inhabitant, meaning that we could increase recycling rate from 46% in 2019 to 65% in 2023. And the blue bag, with the new blue bag with the extension, is already a reality. About 4 million inhabitants in Belgium are able to collect already all plastic packaging. And within 7 months, by the 1st of July, all Belgian citizens will be able to use this new blue bag. And 1st of April, within 5 months, all Flemish people and inhabitants will be able to throw away in the blue bag the plastic packaging. So it's a big increase in recycling of plastic packaging.
Excellent. Thank you, Philippe. A big increase, you say? You are talking about reaching levels of 65%. Nico, at Vanheede, you had some first-hand experience. You were involved in the pilot testing of P+MD. Do you think these are realistic numbers which are being projected?
Well, I will not put into a discussion the numbers. I can only give some experiences that we had. And one of the main experiences that we had is that since the beginning of the project, we have seen an enormous increase of material that we have received. This is for sure, and even more than we have expected. So we have made some expectations in the beginning of the project, together also with Fost Plus. And what we see actually is that in the regions where we are not collecting ourselves, but what the blue bags that we receive from these regions, that these blue bags are coming in mass, let's say. Certainly with COVID, we have seen a bit unforeseen consequences, and there has been an enormous increase also there of household packaging waste that has made the switch, the plastic and other materials, from the normal commingled waste to the blue bags. So it has a positive effect, certainly.
Yeah, so I can hear you say enormous volume increase.
Yeah.
Erik, Indaver is a sorter and recycler for both PMD and now for P+MD. Do you have the same experience?
Yes, indeed. Exactly the same as what Nico is saying. But also let's say the extra fractions that are now collected already. We are sorting them today still in the existing sorting line. We have actually a new sorting line which is ready for operation in March this year, and the volumes there will be on a yearly basis 60,000 tons per year, where today it is more around 30 to 40,000 tons. So there's definitely a big increase, and it will be, of course, now the big challenge. And we've built the installation to do that, to also sort it into good qualitative fractions, and they send these then further to recycling.
Perhaps you mentioned that we need good qualities from these new sorting installations. Steven, you have done some research on the qualities of these streams. Can you comment?
Yes, in the Matter project, in fact, we have analyzed these waste streams, and we have predicted some potential compositions that we might expect in the future. And in fact, what comes out is that the P+MD system will definitely increase the recycling rates. Without talking about the absolute numbers, it will increase the recycling rates for sure. And another positive thing is that, as I mentioned before in one of the talks, is that the qualities of the previously collected fractions does not decrease dramatically. So there's maybe some slight deviations, but not that much. Of course, then there are some new streams that are created. And then we see the PP stream, for example, which some companies already sorted out, which is very nice. In fact, also the PS stream from our models turned out to be a very clean stream in the end, and probably very well recyclable. However, the PS has a bit of disadvantage of scale from packaging. So this makes investment a bit more difficult in this type of recycling, because well, the quantities are just, despite the masses that are created, the quality of them is not so bad. The quantities are not that much that everyone is jumping ready to invest in that.
Yeah, okay, so scale, I hear you say, is very important. I want to turn back again to does any of you gentlemen wish to pick up?
Well, maybe specifically on the PS. Let's say we're quite active in the development of a new recycling technology, also for PS. And we see that there's still a big gap between the volumes you would expect to come available as a waste if you start calculating from what is brought on the market. So normally in Europe, this should be around 750,000 tons of PS packaging waste on the market. However, today we do not see that. And even with, let's say, the next step that we are taking now in Belgium to sort out, basically to collect it from the household and to sort out these fractions, it will still be far below expectations. So there's still room to grow. And I think everything is step by step. But of course, I would like to ask the people here in the room, but also who are looking from behind their computer screen. There is more. There is much more. There's much more to gain, to collect, and so on. So we should think and work about this also, and see how we get these volumes also available for recycling.
Great. I think I want to save you maybe for another question, Nico. We have the first question coming from the audience, which is from a colleague of both of us, Peter Segers from Suez, one of the other waste handlers. And he wants to know, you mentioned that there is a surplus due to COVID in the domestic waste. Do you have numbers on the amount of that, an estimation?
No, I don't have the numbers for this augmentation. No.
Okay.
No.
Never mind.
The only thing that I wanted to add to what have been said here is today what we are seeing, we are living with a kind of a paradigm shift. And it's for sure that not all the materials can be recycled immediately. Not all the plastics can be recycled immediately. But as Vanheede, we have also Vanheede alternative fuels, and we're trying to fill that gap actually. It doesn't mean that the material which is not recycled yet, that nothing is happening with it. So with alternative fuels, we are making pellets for alternative fuel pellets. That's actually.
The non-recyclables.
The non-recyclables, yeah. And these are replacing fossil fuels in industrial applications like cement kilns and so on. But this gives room also to what we are doing here today, that we can create new possibilities, we can develop new technologies for further recycling, actually.
Maybe I want to dig on those new developments and new technologies. Jan, Catalisti has a very good view of which companies want to innovate in what direction. Do you also feel that these questions of how to recycle better and more are alive with your members?
Well, they're definitely alive, because starting from your original question, everybody talked about recycling, but basically what is happening is collection. So collection is increasing and recycling is going to be challenged because the volumes will be higher, and to convert it into reusable material or into fuels or whatever, that's where is the challenge. And I think there are already quite some solutions already proven in this project. But for the future, I know that most of the companies are aware of this problem, and it's became part of their business plan in most of the manufacturers, but also in the end of pipe, in the end of the value chain companies which are active today.
Yeah, exactly.
Would like to add one more thing to this, Jan. There is one step that you did not mention, which is also a very important step there. You have, first of all, the collection, then you have the recycling, but the intermediate step is also the sorting. And this is one of the main key processes within the whole process of recycling plastics. Yeah.
Yeah.
Absolutely. In the meanwhile, there's another question from the audience which I would like to address, and Philippe, I will be sending it your way. Someone asks, and indeed in some municipalities in Belgium there's a pink bag where you can put not only packaging but also some other selected items. And the question comes, how is this related to new P+MD, and would it disturb the packaging stream from new P+MD?
So thank you, Kim, and thank you for the question. The pink bag contains about 85% of plastic packaging, and they will be extended to the new bag because Fost Plus organized the collection for packaging, all packaging materials. So meaning that our first challenge is to make a success about this new blue bag with the extension of the plastic packaging. We are still open and dynamic to find solution in a broad context, but first the key is to have a success with the new sorting plant and to recycle the packaging materials from all packaging.
Okay, thank you. So I can hear both you and Nico just before you saying that the sorting is very important. Maybe I want to pop a next question to our panel. There is in fact, with our northern neighbors in the Netherlands, there is a discussion going on whether post-consumer plastic packaging, whether it should be collected as commingled waste, so together with the other household waste, and then post-separated in the sorting factories, or whether we should really keep to source separation like we have with the P bag and the P+MD bag. And this is also something, before I ask the panel members, which I want to ask you in the poll, and the poll should be appearing on your screen now or soon. Which way do you think we should go with the collection of post-consumer packaging waste? Should we go for the post-sorting, which is cheaper, of course, or for the source separation, which might be expected to change qualities? And here in the panel, I want to ask first our recyclers. Erik, what do you say?
We believe actually that the best thing is that what you can sort at source, keep separated at source, you should do that. And of course, there's nothing is black and white. There might be some situations in specific cities, for example, where it's more difficult to have different fractions at the curbside. But in general, and at the end, as a country, you have to make a choice. I think that the choice overall for Belgium is the best. So separated at source. The effort you need to put in the cleaning of a plastic waste which has been in contact with the normal residual waste, it's so high, this effort, that it's better than that you have maybe some extra collection bag and extra logistics. That does not mean that at the curbside you need to have a bag for PP and then a bag for PS and so on. So still that you can do in a smart way and combine different fractions which are not polluting each other too much. I think that we have a good balance here in Belgium, and let's drive on that further. Yeah.
Nico, I can see you nodding vigorously. May I take it as agreement?
Yeah. I remove my mask. Yeah, I totally agree. It's indeed like Indaver says, waste coming from commingled fractions, and we have seen it in the Profit project, is so contaminated that it's more and more difficult to get it clean, actually. And we should not forget that it's not only the plastic that we are washing when we're talking about mechanical recycling, but we also need to wash our water. So we have to do the water treatment. And this is something which is a lot of times forgotten when we're talking about recycling, that you have also the recycling of water next to it.
Okay, Steven, perhaps this is really dead center in your expertise. What does science say?
Well, science, or the experience that we have is that, well, those who claim that the qualities can be equal, I find it hard to believe from what we see, from the experience in the different projects. I know there is also some of these comments on the comparison between source separation and post separation is about odor. Well, I can say that they both stink. and they are both difficult to deodorize, so you have to put a big effort in both streams to deodorize, but you create a whole bunch of other problems like wood, fibers, textiles, toys, and so on. And in a discussion where we at the end also want to have food contact recycling, I think it is maybe not the best idea to stop the source separation system that we have now and that somehow functions in a good way. Maybe one point I wanted to make on the source separation system and the extension of the P+MD to P+MD from the last part is that there is indeed, we might expect a delay between the actual recycling rates increase figures and the decision to do the extensive collection of the P+MD.
Is this because there's a learning curve involved?
Well, it's a bit chicken and egg. Do you first collect the waste and then invest, or do you first invest and then start collecting for that? And I think in this case, there is the choice has been made to now first extend and then extend it back and then make the investments, which I think is the most logic choice. So I will see that. I think we will see gradually increasing the recycling rates in the coming 5 years, or at least that's what we hope.
Let's have a look what our professional audience of today thinks, if we can have the results of the poll. And then I see that we have an overwhelming vote for the separately collection. Thank you for giving us that input. Perhaps maybe to round up that discussion, Philippe, if such a decision would be made to which way should we go, Fost Plus will clearly have a large role to play. The experts would stick to source separation. The audience, who is professional, says the same. Do you agree?
Yes, I think Fost Plus fully align on that. It's also our first option to have selective collection for the quality reason, and we have a high demand for our sorted bale and to have as much quality on the application. This being said, we still think there is maybe a room to collect and to recycle even more for such area like out of home. When we are in public areas, we know that we try to have good quality. It's very difficult to get good quality, and maybe there are some opportunities there to use post-separation.
Like from bins in the street, for example?
From bins in the street, there are materials coming there that we challenge and get difficulty to get them, and maybe their post-separation could be a solution.
Okay, thank you. I think that the panel is quite unanimous on that one. I want to move to a next question, which was also relevant to the project results which we showed. We have, in Matter, as one of the first projects, we have made a comparison between value for money, value for technology, for mechanical recycling versus chemical recycling. This is a question which lives, I think, very strongly within industry, and I'm going to be asking my panel members about that, but I also want to ask you, how do you see this evolution, the coming of more chemical recycling? Do you feel that this is complementary to mechanical recycling, or do you feel that this would be, in fact, competitive? Let us know, and we'll bring that into the debate in a little bit. Jan, perhaps I want to start with you, as Catalisti has a good overarching view of the sector. Have you got a feel for what your members think on this?
Well, like you indicate, we are, let's say, our members are both coming from the end of the value chain as the beginning of the value chain. And as you were a guest last week on the Essentia event, it was clearly expressed that from that side, the more you go to the chemical companies, the interest in chemical recycling is quite high. To go more to the base molecules and to build it up again to new plastics and to new polymers. On the other hand, I think it's an and situation, that the interest is both in mechanical and chemical recycling, and perhaps if there is room for that plastics that can't be recycled, for other solutions like take to the metal industry or the cement industry. But in all of these topics, there needs some innovation, I think, to improve the process and to go to a higher yield and higher efficiency.
Okay, that's clear. Maybe Erik, Indaver is one of the few companies who is active on both sides, both on mechanical and chemical, so you should have a unique view on this.
Yeah, try to share our unique view. Yeah, basically, mechanical recycling is existing already for many, many years. And there's definitely a reason of existence, and that will stay. I think also there's room to improve. There's room to increase the volumes and can go to mechanical recycling. You see also that there, in terms of technology, there's still some steps to make. But on the other hand, we also believe that there is a limit to it. Then actually the chemical recycling comes around the corner. Because the limit of the mechanical recycling is that, okay, you can wash, you can clean, you have melt filters and so on, but you will never be able to get into the, let's say, the structure, the matrix of the polymers. And that's something that the chemical recycling can do. You can really break it down to the backbones of the polymers and take out also the fillers and things like that. That's one thing. A second thing is that mechanical recycling has some difficulties for some plastics, like polyolefins, for example, to recycle back into food grades. And yeah,
is it a difficulty or is it a legislative challenge? Is it technical or legislative or both?
I think the future will prove it. Today, you see that there is still some developments in it, but it's also a technical issue. There are some plastics who absorb much easier some particles, contamination than other plastics. And the ones that absorb it easily, they will, I don't think they will get to the level that they can go back into food grade. But for these plastics, there is actually the chemical recycling also. The only thing is chemical recycling, it's really at the beginning, it's at the start. So there's still a lot of steps that needs to be taken. And now we are at the level of demonstration units.
Absolutely. If we talk about processes and their limits and how they can be demonstrated, Steven, that brings me back to you. How do you feel about this?
Well, it's a difficult discussion, but I would like to make maybe a blunt statement, is that I think they might be competitive in a way, because the hard reality is that they both like clean feedstock. So some people say the chemical recycling, they will take the rest of the mechanical recycling, but the truth is that chemical recycling also doesn't like contamination. Of course, the big benefit that you have with mechanical recycling, you do a pre-treatment, you remove some contaminants, but as Erik already mentioned, you cannot touch the core of what is in there, or it's very difficult to do so. And this is possible in chemical recycling. So you can do downstream processing of the, for example, pyrolysis oil that you make, and you can clean off the other things. So that's an advantage. Of course, then you talk about downstream processing, and every separation process decreases the yield. So you create less valuable product, and your economic balance get a bit down. So the reality is that the more contaminated your input stream, the more difficult it is also to make chemical recycling competitive. This said, does not mean that we have to make a choice. I think still they can coexist together. And this might also depend on the economic balance on a regional scale. There might be other factors, or they might work together in a way, because also maybe the washing process of mechanical recycling can serve as pre-treatment for chemical recycling. So as Erik also mentioned, the future will show us a lot on that. But that they are completely that thermochemical recycling will take the rest, that is a bit difficult to believe for me, as they also face the difficulties with this contamination.
Okay, interesting. So we're getting a spectrum of opinions here. Let's see what you think at home. Could I have the results of the poll? And there we see that an overwhelming majority has said that they are complementary. Maybe this is a should be complementary. Maybe I can translate it like that. And so a lot of people see space for them to coexist. Maybe Nico, you could comment on this. Vanheede is a company mostly active towards mechanical recycling.
Yeah.
Do you, what Steven said, that there might be some threat to your feedstock, would you experience that?
Well, certainly, yeah. I mean, they are complementary, but there will be some cannibalization. You cannot expect that it will not happen. The thing is that, and I repeat it, that it will be complementary because, as Steven also mentioned, separation, delivering good qualities to these installations will be key and is very important. And this gives also opportunities for companies like ours. So. On the one hand, I say yeah, but on the other hand, I say there are plenty of other opportunities and new opportunities for our company too.
Okay, so it's a big pond for you to fish in.
A big pond, how should I say? Certainly, the incoming materials, as we already discussed, are becoming much bigger. Actually, the quantities. So indeed, yeah, we can still have our place in the whole circular plastic economy. Absolutely.
Okay. Philippe, maybe I want to ask you a nasty question on this. Does Fost Plus care whether it is mechanically or chemical recycled? Does it matter to you?
Thank you, Kim, for your question. I first want to say that we have, as Fost Plus and in Belgium, high ambitious targets for recycling rate, as Europe has, and both solutions are important to meet the target. And today, if we would only keep with mechanical recycling, we don't believe we will reach higher targets. So we think chemical recycling has a role to play in order to help us to reach even a higher target. And okay, today they are probably mostly, like you all said, complementary because they are usually a pre-treatment needed with a mechanical recycling, and then after chemical recycling. There are also some rejects from mechanical recycling that could be used in chemical recycling. So I think both technology will help us to reach a high target.
Thanks. In the meanwhile, there's a question from the audience that is picking up on something which you said, Erik, the food contact grades. So a question which we get is, do you see a future in food applications for post-consumer plastic waste?
To chemical recycling, yes. I mean, if you take the example of polyolefins, if you depolymerize them, you can produce some kind of a naphtha. And this naphtha, before it gets back into, let's say, ethylene, propylene, and then at the end polyethylene and so on, you need to go to a steam cracker. So that's existing technology. We know how this works, and it's really taking out, well, let's say the process before where you're producing the recycled naphtha is already taking out a lot of contaminants. But at the end, when the food applications will get a polyethylene, which is produced from a recycled naphtha or is produced from a normal naphtha, they will not see the difference in terms of quality. So, yes.
Okay, that's a clear answer. Yeah. Perhaps I want to go back to an aspect that was touched upon during the presentations of the project, that was value chain cooperation. Both of these projects, Profit and Matter, have been Catalisti-ICON projects, which is a very specific format. Perhaps I should ask, this type of project in which academia and industry can work very closely together and to some degree be funded for that, how important is that for the industry? Since you still have your mask off, Erik, I will start with you.
Yeah, I have a very difficult mask to put on, and so that's why I keep it off. No, but basically it is important. and okay, we are not going to say that we don't like some extra funding. That's always welcome, let's say. That's one reason, but I think as important is the fact that if you think in towards circular economy, I mean, you cannot do it by yourself. It's a true circle, and there's not one company who is actually managing the complete chain. So you need to cooperate with other companies, you need to cooperate with knowledge centers, with academic partners and so on. To be honest, as Indaver, we didn't really have a clue towards all the, let's say, the expertise that there was within the knowledge centers and the academic partners. And therefore, it's definitely a big help that an association like Catalisti is looking for these partners and bringing them together by the calls that they are making. So that works very well, and it helped us a lot to get the right parties on the table. Otherwise, I don't think we would have been sitting here smiling with the success of Matter.
True. Maybe for profit, Nico, can you comment? How important was it for you as Vanheede?
Well, it has been proven that it was very important, and I share the opinion of Erik. If you want to create a plastic circular economy, you need all the parts of the chain, and you as an academic partner, you play a very important role. I always say you can do some testing and let's say hobby cooking, like at home. But if you want to prepare a meal, a restaurant meal, well, you have to get the experience of the other people, and you are the experts on this. So yeah, very important, and also thank you to Catalisti to add this in this matter. For us, it's not only, and like Erik also said, not only the money which is important. It plays a big role. If you can fund or if you can get funding from the Flemish government, this is important. But in first instance, I must say the cooperation is the most important of this. Okay. Absolutely.
Let's pop that to Michelin star chef Steven. In this analogy, how important is it for the universities?
I do like good food, and that's in first instance. But in general, it's very important. I think this Catalisti and this ICON type of project, because there we have the ability to really collaborate with industry. It's 2 years or 3 years project. It's challenging. It pushed us to the boundary, but somehow it's also nice, and this collaboration with a set of companies to together approach a problem that is very, very important for us. And now also there is a new moonshot program, which in fact allows also, which will give a big leverage to Flanders becoming, or even becoming further, the front runner in research related to circular economy. And this also allows a bit more fundamental research, a bit at the lower TRL levels, which up front was maybe not so, for some researchers, that do fundamental science was a bit more difficult to access this ICON project. So in that sense, I think in Flanders we should be lucky with Catalisti. And I want to also offer my gratitude here that Profit and Matter were both approved, and also the process to write such projects together with Catalisti is really fluent and searching partners together. And also thanks, of course, to the people of maybe this is not the right moment, but also thanks to the people of LIO, of course, because they organize the review process, and they are sometimes a bit in the shadow working maybe for some, but they organize the review process and in the end provide the money together with the ministers that decide on that. So I think in Flanders we are very or at least and I think many of my colleagues are happy with Catalisti and the leverage that is offered in this way.
Okay, Jan, this is a lot of flowers falling at your feet. Can you comment maybe at the same time about how relevant is this ICON channel, but how does it play a role vis-à-vis Moonshot, where Catalisti also has a big role?
I think the core of the added value of the ICON project type is already explained, and also by Steven. But summarized, it's a unique tool that is not existing everywhere else in Europe. It's focusing on cooperation, open innovation between companies. And this is the field of activity here is a good example there, because it is a challenge for every company which were in all these projects outside of their comfort zone, but with a high added value in the end of the project. So adding know-how and knowledge was extremely important over the value chain with big companies like Indaver and also smaller companies that were in the consortia. And then with the added value of the expertise of the academic players that can bring basic know-how into this project. So that's the core and the strength of an ICON project. Now, related to Moonshot, basically Moonshot is going one step back and wants to build basic know-how, strategic knowledge, industry-related, in this case, on circularity. And the future will show that after all these Moonshot projects that already approved, and recently and even last week, there were some new projects approved, they will end up in new ICON projects, where again companies, some of them are sitting here in the panel, but probably also others which are now listening and watching, they will join also these kind of projects. And then we will have new ICONs where part is subsidized by the government, but a lot of activity and efforts will be done by the companies themselves. So it's, let's say, a circular approach, build some basic know-how, attract the companies on these topics that they indicate that are important, build some strength, basic strength, and then go into some applicable projects.
Okay, so the innovation train is really at full speed.
I wouldn't say he's at full speed, but he's like a diesel, he's getting on track. And it's still a challenge to accelerate.
Excellent. Perhaps I want to skip to the European context. We are getting a lot of questions from the audience which relate to this European context. And yeah, let's talk policy and let's talk tax. Like everybody in the audience also knows, in July, a tax was voted, a European tax of €800 per ton of non-recycled plastic, which will be in effect from January 2021. There is a lot of discussion going on to which degree this will in fact be beneficial to the circularity of plastics and to the plastics industry. And we have a final poll which we want to launch on that. What do you feel, where will it go? Will this be beneficial to plastics recycling industry? Not at all, or will it really not have a netto effect? Let us know and we'll take it into the panel discussion in a minute. Perhaps Philippe, I can start with you for this question, because you are closer to the policy level, if I can call it like that. How are you experiencing the effects this tax may have?
Thank you, Kim. First of all, unfortunately, this tax will not be allocated to the circular economy. So meaning this money will not be used to be reinvested in the circular economy. And we think it's a missed opportunity, because it takes funds from companies that they would have been able to maybe invest in circularity, and this money is not allocated for that. Knowing that with the green dot contribution, there will be an enormous increase of about 200 million euro will be paid by the members of Fost Plus, by the company, to set up the implementation of the blue bag, the new sorting plan, and the recycling plan. So there is already enormous money to be invested thanks to the green dot fees.
Okay, perhaps Erik, Indaver is a company which is active in several European countries. Yeah. How do you place this tax? Would you agree that the earmarking is required, or?
Yeah, I think it's in a way it's a bit a missed chance. Okay, I understand that it's a way to generate some extra money on the European level, and I hope in some way that it will flow back to the initiatives which are related directly to recycling. But today, that's definitely not sure that this will happen. So it's a big question mark. In my opinion, there's better ways to increase recycling rates. For example, blend-in quota.
Could you maybe give us some more details on that? Because that's also a question we got from the audience. Yeah. How relevant would recycled content be?
Yeah, it's very relevant. I think it would solve a lot of problems. We would win a lot of time. Because then, in a way, you are creating a market for recycled products immediately. There will be a demand, and from the companies who at the end are producing packaging material and other types of plastic applications. And there will be a huge demand depending on how big this blend-in quota are. Is it Is it 25%? Is it 30%? Is it 40%? Big question. But there will be really a pull from, for example, the polyolefin industry, the polystyrene industry, and so on, to have recycled material so they can include it in their new products.
Yeah, maybe we also got a question, and as we know, the recycled market is under a lot of price pressure from the virgin plastics market. Is what you are proposing, could it be, maybe Nico, you could take this one, do you think this could be a way to alleviate that pressure? The price competition which we have with virgin, do you think?
Yeah. Well, I also think that the tax on plastic should not be used only for taxing. And this is a bit the feeling that we all have around the table here, I think, if I may speak for all of you. But it also can give some, create some opportunities on the market. We only have to look, for instance, at the UK. So we all talk about Brexit and so on, but I've seen some good things there. There they say, we will tax £200 per ton on materials coming to the market which does not contain more than 30% of...
which contains less than 30%.
Less than 30% recycled content. And this is a bit another way, as Erik says, or you oblige it, or you force it by punishing the other ones. And I think there, if we can take this opportunity to do it like this, I mean, there is a big chance that we can get the motor started. But taxing for taxing, it's not a good idea, I mean, in my opinion, no.
Yeah, it's interesting that you bring up the British example, because indeed, once this 30% almost as a ghost started going around the industry, you could hear a lot of companies, brand owners who were interested in already starting to increase this 30%, even before such a law was effectively there. I wonder, here in Flanders, Jan, if the companies who are active here, what has their response been to the announcement of this new tax?
Well, I'm not that well positioned to answer in their name. But on the other hand, I do think that it is still a challenge for most of the companies to increase recycled content. And we all are aware that it's a matter of sustainability. It's a societal aspect that we want to tackle by either keeping carbon in the loop, and on the other hand, by taxing it or by squeezing it into some kind of a corner. And that's still what I think is under discussed at this moment in view of the economics today, of the oil price today, of the future. We are in an industry that's in a transition. And the total picture should be looked into more detail, and it will definitely happen in the next decade, I think. Yeah. And every company is looking at it, but doesn't have a clear answer on it. It's still in the following mode instead of in the adapting mode, I think.
Yeah, there's still a lot of fog to lift there.
Yes.
Maybe if I can just
briefly, because I want to
on
launch
this
something.
Recycled content, I mean, there's another thing also, because companies might say, okay, if we need to do that, then it will make life difficult for us, and we need to change our processes and so on. But there's one thing which is now pretty clear within Europe, that is that we want to be carbon neutral by 2050. By having this recycled content, for example, for the polystyrene, we have been doing a lot of LCAs now recently. You have a possibility to actually have a net avoidance by using recycled polystyrene in your polymerization. And that's, I believe, for these companies much easier to save on CO2 than, for example, start changing their own process. Yeah. So there will be a drive for that besides just recycled content.
Okay, that is an interesting point of view. We only have a few minutes left, so I think I want to look a little to the future with the last poll of today. And then I will also ask the members of the panel. I forgot to show the results of the previous poll. Sorry, can I have them up on screen? Yeah, so there we had, well, a majority thinks that still we can turn this to an advantage for the plastics recycling industry, over 50% if I see correctly. And remarkably, some people think that there will be no effect. So maybe we can take that as a balance of everything which has been said here. Let me launch our final poll before I ask the panel members. If we look to the future, we saw some project results here today, but I would like to ask which aspects of packaging would you think are most critical to be tackled next in terms of recyclability? Where do we need to focus our research? Well, I'll let you answer this at home. Perhaps, Steven, do you think there's still any low-hanging fruit to be had?
Well, to be honest, if there would be low-hanging fruit, probably it would have been picked. So I think, as we hear here and see in the project results, is that the challenge is so complex and there's so many different issues together to tackle that it's hard to define a low-hanging fruit. I think that's a combination of measures that we need, and I think specifically about 4 things. So the first thing is that the incoming mix has to be simplified, because the waste as it comes now on the market is a whole diversity of things, and it's very a mix of polymers, a mix of additives, which is needed, of course, for the functionality. I understand that, and I don't claim everything to be monolayer or everything to be too much simplified that the function is endangered, but at least there should be some minimization in the diversity that we currently have. And secondly, a bit linked to that, is transparency throughout the chain. Because if you recycle, if you get the waste in your door, you really don't know what is in there. And I give you the example of de-inking. So we try to de-ink, but finding out what is the composition of the ink is a whole challenge. That I can tell you. You go to the converter who doesn't know. You then go to the ink producer who knows the composition of the ink, but not of the adhesive that is in the ink, for example. So that's a very difficult thing to find out, this transparency throughout the chain. I think that would really facilitate, and I understand the competitiveness issue there, but of course I think on the longer term we need to, well, be a bit more open in that.
Okay, I'm going to have to...
Okay,
sorry,
I was
short,
you stopped me.
but I will take the essence away from you. Is still cooperate in the value chain. If we go more to the selection we made on technical topics, can I see the results of the poll? Then I think there's an overwhelming response that multi-layers should be next to be tackled. Jan, if I can ask, is this also what you see coming from your members?
Well, not only from our members, it's also if we look to the moonshot topics that we are tackling today, which are basically set by the companies. Well, we see the multi-layer and multi-component materials is the highest challenge. But also the others which are there are popping up. I think if you look to the moonshot targets that are set, it's on multi-layer, it's on traceability of components and easy separation focus. So it's an end-end situation again, but the main focus is again on multi-layer, and that the challenge is also to combine it with design to recycle.
Yes, absolutely. I think we are nearing the end of the event. I will ask each of the panel members in turn, and I will start with you in a moment, to give me in one sentence the core message which they feel they still want to deliver to our audience of today with regard to plastic circularity. This can be: where should we go? What should we notice? What should we do for the future of true circular plastics? Philippe, may I start with you?
I want to say also that we still need to collect even more in company. We have a lot of P+MD in company, and out of home we are champion at home sorting, but we still have some challenge there, and that's my message for today.
Thank you. Nico?
Well, the most important message, and also a bit low-hanging fruit there, is that we should favorize the use of recycled plastics in the industrial chain. This is my message, and I will stand by this.
Thank you. Erik?
Same as Nico. And also, I would like to add, I mean, there's many projects which are, let's say, ready, which are on the table. And it's just a matter of, let's say, a little bit of taking a little bit of extra risk and jump, not in a hole, We are not jumping in a hole, jumping in a, let's say, a demo plant, for example, where you know that after a successful demo plant, you can go to such economy of scale that also for industrial partners, there's definitely a good return to these projects. So let's focus on the next step. If we are, let's say, thinking about putting the money on the table, the next step is totally different. It will be a new type of economy, but there the returns will be there.
Okay, thank you. Jan?
I think I can only support what Erik is saying. I think we should focus on those technologies that are there and bring them as soon as possible to maturity, bring them into demo, into pilot plants. And the projects which are on the running and which will be implemented within 10, 15 years, they will be completely different. I'm convinced of that. And let's say research is going on. And for the time being, go for the low-hanging or medium-hanging fruit, implement, find the money, and that's where we have to go, I think.
Okay, thank you, Jan. Steven?
Well, I would somehow join this message. The situation is complex, many challenges, but on the other hand, if you see how everyone is getting involved in it and how everyone pushes for it, I'm moderately optimistic that in a period of 5 to 10 years, we might have solved really a lot, and that probably plastics can have polished their image, which is currently a bit damaged based on all these challenges that are there. So based on research, collaboration, and investments, and industries that are willing to stick out their neck and actually do it, which is currently the last few years really incredibly increased. I'm moderately optimistic that we can solve this thing in 1 decennium, I would say.
Okay, thank you. That's some optimism to end with. I had a lot more questions to ask these panel members, as I'm sure you at home also did, but this is all we have time for. So this was our closing event of Profit and Matter today. There will be a link sent to you where you can watch again this entire event online. So all I can do now is to thank the people who presented today, is to thank the members of the panel here today, Philippe, Nico, Erik, Jan and Steven, and also to thank you, the viewers at home, for interacting with us and for being interested in bringing plastic circularity to the next level. That was it for us today. Thank you. See you next time.